The kinetic energy of the Peppa Pig family car is definitely a question you've all asked yourselves at one point. However, what is the kinetic energy of the Peppa Pig family car? Quick disclaimer, I actually had a whole team of friends work on this with me, and we have a very long email stream to show for it. Anyway, on to the video. To figure out the kinetic energy of a moving object, you need to use the formula half of mv squared, which is in other words, half of the mass times the velocity squared. This means we need the weight of the car and the speed of the car. Let's start with the weight. If you look at the Peppa Pig car, it doesn't match any model in the real world, but we can create an estimate based on the closest model. My friends and I scoured far and wide across the internet and managed to end up with the 1974 Volkswagen Beetle, which weighs around 816 kilograms. Now that we have the weight of the car, we need the weight of the family. How could we possibly do that, you might ask? Well, we only need the ages of each member. George is 2, Peppa is 4, and while it is impossible to determine the ages of Mommy and Daddy Pig, most people assume their ages to be 26 and 30, respectively, which makes both of them the oldest pigs ever. Now, using this chart, George appears to be around 74 pounds, or 33 kilograms, and now we have the formula for the weight of a pig using its age, which is W equals 3 outside of A minus 2.9 plus 105. By plugging the family's ages into this formula and converting the pounds to kilograms, we have Peppa Pig at 49.1 kilograms, Mummy Pig is 79.1 kilograms, and Daddy Pig is 84.5 kilograms, contrary to the popular belief he's 500 pounds. We can finally add these together to get 245.7 kilograms. Adding that to the weight of the car, we get 1061.7 kilograms. On to the speed of the car. We can use the circumference of the tires and then multiply it by the rotations per hour to get the distance covered in that time and therefore the speed. Using this image, we have Peppa Pig standing next to the family car, and we can figure out the radius of the tires this way. A quick Google search gives us a height of 3 foot 9 inches, and by drawing a 440 pixel line next to Peppa, we have 3 foot 9 equals 440 pixels. By dividing this length by Peppa's 45 inches, we get 1 inch equals 9.8 pixels. By using another line, we measure the diameter of the tires to be 136 pixels, or 13.9 inches, or 35.3 centimeters. This means the radius is 17.7 centimeters, and using the formula 2 pi r, the circumference turns out to be 111.2 centimeters. We now need the RPM of the tires. We can watch the car and time how long each rotation of the tires takes, but the only visual indicator for the rotation of a tire is this tiny bump that I can only assume is a singular rotation. So by converting the video of the tires bouncing into a GIF, I can count the amount of frames it takes for one rotation, and that is 5 frames, or in other words, a sixth of a second. I just realized what I said, and that sounds so dumb. Anyway, this means the rotations per second of the tires is 6, and the rotations per hour of the tires is 21,600. Multiply this by the 111.2 centimeter circumference of the tires, we get 24 kilometers an hour, which means this car is driving very slowly. We can now finally use the kinetic energy formula for our car, where half times 1061.7 times 24 squared would equal, drumroll please, 305,769.6 joules, or 305.8 kilojoules, for the average cruising speed of the Peppa Pig car. But wait, there's more. That's just the average speed. What about the top speed? According to this website called It Still Runs, we'd get a top speed of 86 miles per hour, or 138.4 kilometers an hour. By applying this to the formula, our new kinetic energy for the top speed of a car is 10,168,198.2 joules, or 10,168.2 kilojoules. But hey, that's just a theory. A stupid theory. Thanks for watching this video. Now go do something productive with your life other than watch my depressing YouTube channel. Goodbye.